In this lecture presentation, we talk about the relationship between work and energy. So it turns out that work and energy are tied closely together, and that the distance over which an object moves when a force is applied leads to a change in kinetic energy. So if you think about Newton's second law of motion, F equals ma, if there is a net force acting on an object, that means that there's an acceleration. And if there's acceleration, that means that the velocity of the object is changing in some way. And so the work-energy theorem is just another way of looking at motion, specifically sort of looking at it as it's tied to Newton's laws of motion, and saying that if we could figure out the work that's done by that applied force, that the end result is going to be a change in the kinetic energy. And it turns out that the relationship is such that the work is exactly equal to the change in kinetic energy. So if there's a force applied and that force is doing work on an object, the end result is the amount of work that's done by that force is going to exactly equal the change in kinetic energy. And that work can be done by any force. It can be done by the force of gravity. It could be done by an applied force. It could be done even by friction, for example. One of the things that we know is that if an object starts from rest, and we were to double the speed of an object, it requires 4 times the amount of work as if you were just making it move at a particular speed. So by doubling the speed, you basically increase the amount of work by 4 times. And that's based on what happens to the kinetic energy. So if you double the speed of an object, the kinetic energy actually increases by a factor of 4. So you could think about how much work is required to change the speed of an object by looking at what would happen to the kinetic energy if you wanted to change the speed of the object. But let's focus more on this work-energy theorem or work-energy relationship, and let's see what we can do in terms of how we could apply this. So the first thing is that we could write out what change in kinetic energy is, right? So the work here is the work done by some applied force on an object, and the end result is a change in kinetic energy. Well, change in anything is the final value minus the initial value, so the final kinetic energy minus the initial kinetic energy. And so what we're saying is that the work is equal to the final kinetic energy, 1/2 mv final squared, minus the initial kinetic energy, which is 1/2 mv initial squared. If we use the basic definition of work, where work is force times distance, we could plug in that value into the work-energy theorem, and we could say that the work, which is the force times the distance applied, where that force has to be along the direction of the motion, is just going to equal the change in kinetic energy. So what we have now is a way of looking at the motion of an object. Instead of looking at it in terms of Newton's second law and looking at it in terms of the definition of acceleration, we could just look at an object, and if we could figure out how much work is being done on that object, then we can figure out what's going to happen to the motion of the object. In other words, I can look at if an object starts from rest and I do some amount of work on the object, I can figure out how fast that object is moving afterwards, according to this work-energy relationship. So here is an animation, and it's just going to keep repeating itself, so I apologize for that. But basically you have a skier that's starting at the top of a slope. And you'll notice that the slope here is very, very smooth, but then when they get to the bottom where the snow is not packed very well, it looks kind of rough. So the person starts off at the top, and if you follow this, they have potential energy, and as they go down, the potential energy is decreasing. And as the potential energy is decreasing, as they fall, the kinetic energy is increasing. So let me try to talk through this. So we've got kinetic energy, potential energy, and then work. So we start off with potential energy, and the potential energy drops as the person goes down. and the kinetic energy increases. And then when they hit the packed snow, we have some negative work that's being done because there's friction and the object slows down. So, I'm going to talk through this, and I know it's going to just keep going, but I'm just going to pretend that my pointer here is the actual person. So the person starts off at the top. They have potential energy, and there is work that's done by gravity, because potential energy is work that's done by gravity. As the person falls, there is work done by gravity. Because there is work done by gravity, work is equal to change in kinetic energy. So the person starts from rest. As work is being done by gravity, that means there's a change in kinetic energy. So person starts off with 0 kinetic energy. Work is being done, so now they are gaining kinetic energy as they go down the incline. When they get to the unpacked snow, they're traveling at some speed, so they have kinetic energy, but the unpacked snow causes them to slow down, right? Because it's like friction, it's like a rough surface. And so there's also work being done because they're now in contact with a rough surface. And the work that's being done here is actually negative work because the force that's being applied on the skier in the rough part here is opposite the motion. And so they have kinetic energy, and then by the time they get to the end, they have 0 kinetic energy. So the initial kinetic energy is positive, the final kinetic energy is 0, so the work done in this case is actually going to be negative. And when they go across that unpacked snow, the work down here is going to be a negative value. And as the work is negative, the kinetic energy drops. It gets slower and slower and slower. So this is an example of the work-energy theorem in terms of sort of a visualization of what's going on. So let's try to apply an example. So in a previous lecture, we had Juliet, and she pushed a crate, a 1 kilogram crate, across a level surface with a force of 3 newtons for a distance of 2 meters. And we can figure out how much work is done on the crate by Juliet. So we talked about this before in a previous lecture, and here's our picture of what's going on. Here's our applied force of 3 newtons. We know that the weight and the support force do not contribute to the work because they're not helping it move along the direction of the motion, which is to the right. So the work is the force times the distance. Force is 3 newtons, distance of 2 meters. So the work that is done on the crate by Juliet is 6 joules. Assuming that the crate starts from rest, what is the speed of the crate after it has traveled 2 meters? So here we want to figure out, how fast is it going? So this is similar to other examples that you may have seen when you talked about Newton's second law. So certainly another approach to this would be there's a net force, so there has to be an acceleration. So you could use F equals ma. You could find the acceleration. And then once you knew the acceleration, then maybe you could figure out how fast the object was going after it had traveled a certain distance. But we're going to do this a different way. So we're going to use this work-energy relationship, which says that the work that's done on the crate is equal to the final kinetic energy minus the initial kinetic energy. And so we know that the work that's done is 6 joules of work, because we calculated that. We're trying to figure out how fast this crate is moving after it has traveled the 2 meters. So this is 1/2 the mass times the final speed squared. That's my final kinetic energy. And then minus my initial kinetic energy. Well, my initial speed is 0. So if I put 0 in here, 0 times anything is 0. So my initial kinetic energy, if it starts from rest, this term is just 0. So 6 is equal to 1/2 of 1. Well, 1/2 of 1 is 0.5. So I have 6 joules is equal to 0.5 times the speed squared. I can divide both sides by 0.5 to cancel it out on the right. And then I will have isolated my speed squared. So 6 divided by 0.5 is 12 joules over kilograms is meters squared over seconds squared, and that's equal to the final speed squared. I'm not done yet because that's not how fast it's going. That's still squared, so I have to take the square root of 12, and I get 3.46 meters per second. So by figuring out the work that was done on the crate, I could figure out also how fast the crate was moving after it had traveled that distance of 2 meters. And that's pretty powerful. I didn't have to really know anything else. I could use basically one expression. It's all scalar quantities. I'm not dealing with vectors in this case, as long as my force that's being applied is parallel to the direction of the motion. So one of the reasons that we spend some time talking about this work-energy relationship is because we can define something called the total mechanical energy of a system. And the total mechanical energy of a system is defined as the addition of the potential energy and the kinetic energies together. So the total mechanical energy of a system is the kinetic energy plus the potential energy, where, remember, potential energy is just the work that's done by gravity. So it turns out that in the absence of any external input or output of work other than work that's done by gravity, the total energy of a system remains unchanged. So what does that mean? So basically, you can have a system that has potential energy, and similar to the picture that we looked at previously, so I'm going to go ahead and flip back a couple slides for a second. There we go. So we have a system that has potential energy, and as it falls, it's converting, the potential energy is decreasing and the kinetic energy is increasing. And so along that incline, the only work that's being done is work that's being done by gravity. So mechanical energy is this combination of kinetic and potential energy. So in the absence of any other forces other than the force of gravity, the potential energy plus the kinetic energy is going to remain unchanged. And we can say that energy is conserved, or that energy cannot be created or destroyed. So if something is conserved, that basically means that it's going to stay the same. And so that's a pretty powerful thing, and we can actually use that idea that energy remains constant, mechanical energy remains constant, in order to solve some problems as we look at motion. So here's a picture of a simple pendulum, and I'm going to start it's actually a video, I'm going to start it in a second. So the pendulum is pulled back, and over here on the picture I have the total energy of the system, and then I have a line that represents the potential energy, and I have a line that represents the kinetic energy. So the kinetic energy is going to be green, the potential energy is going to be blue, and the total energy is actually going to change, it's going to change color. Right now, this pendulum is pulled back and it has potential energy because it is raised above its lowest position. So if I let the pendulum go, its lowest position is going to be somewhere over here, and I have raised it above that lowest position, so it has potential energy, and all of the energy that it has is potential energy. But once I hit the start button, maybe on here somewhere, oops, hold on. All right, there we go. So once I hit the play button, we can see what's going to happen, and I have this in a slow motion mode so that we can see it. So as this is released, the potential energy decreases. When it gets to the bottom, it has a lot of kinetic energy, and then it loses all that kinetic energy, so it's got kinetic energy, losing kinetic, gaining potential, losing potential and gaining kinetic, all kinetic at the bottom, and then it gets all the way back over to the other side. It has all potential. And so as it moves back and forth, it has a combination of potential and kinetic. At its maximum position, It has all potential energy. As it falls down, it loses potential energy and gains kinetic. At the very lowest position, it has lost all of its potential energy, and that has been converted into kinetic energy. And then as it goes back up to the other side, it loses kinetic and gains potential. But one of the things that you should have noticed, and I'm going to hit play again, is that the total energy of the system has remained the same throughout the entire motion. So watch the energy. The total energy is the same, but it's turning from green to blue because it's converting between kinetic and potential, but the total of those two added together is still the same value the entire time, right? So losing potential, which is blue, gaining kinetic, gaining potential, losing kinetic. All right, so let's look at an example. So this is kind of a long example, but I think it's worth taking the time to go through. So Alice drops, meaning from rest, a 2-kilogram rock from a cliff that's 2 meters high. We want to fill in the table below, assuming that there's no air resistance and that the acceleration due to gravity is 10 meters per second squared. So basically, at these different heights, we want to determine what is the potential energy, what is the kinetic energy, what is the total energy, and how fast is this rock moving. So in talking about motion in previous lectures, you certainly had objects which were dropped, and you could figure out how far they fell and how fast they were going in certain intervals of time. And so we're going to do something similar to this, except we don't have any time intervals. We're looking at distances covered and seeing if we can figure out how fast that rock is traveling at these different positions by applying energy. So we've got the 2-kilogram block. It's at the highest point and it starts from rest. And we know that the total energy of the system is the addition of the kinetic plus the potential. So the first thing that we know is that we're going to start at the very top, the 20-meter mark, and we're raised above, that reference of 0. And we know that at the very top, the rock is dropped. So we can fill in our table, and we know that the speed initially is 0. If the speed is initially 0, that tells me that the kinetic energy is also 0 at the top, because the object is not in motion yet. It's starting from rest, and so since the kinetic energy depends on the speed, if the speed is 0, the kinetic energy is 0. Anytime we know how high an object is above the reference point, we can calculate its potential energy. So the potential energy is mass times gravity times the height. So it's 2 kilograms times 10 meters per second squared, which is our gravity value, and then our height is 20 meters. So this gives us 400 joules. So at this top point, the amount of potential energy is 400 joules. We now know the kinetic energy and the potential energy, so we can solve for the total energy of the system, which is just the kinetic, 0, plus the potential, which is 400. So the total energy of the system is 400 joules. So I have filled in my table, and I have figured out what the potential, kinetic, and the total energy of my system is. So in this particular case, the only force that's acting on this rock is the force of gravity. And so the only work that's being done is work that's being done by gravity, but we know that that's taken into account by this potential energy term. So other than the force of gravity, there are no other forces that are acting on this rock, and therefore I can say that energy is conserved. So if energy is conserved, that means that the total energy of the system remains unchanged, which means that if I'm at the 15-meter mark, the 10-meter mark, the 5-meter mark, or basically right before it hits the ground, all of those energy values are going to be exactly the same. That's what it means to say that energy is conserved. The total energy of a system remains constant throughout the motion. So the good news is once I find the total energy at one point, I know what the total energy is at all points along the motion. All right, so now my rock has moved down to the 15-meter mark, and I want to know what is the potential energy, kinetic energy, and the speed. So obviously my rock is now moving, right? It has some speed associated with it. I don't know what the kinetic energy is at this point, and I don't know what the speed is. So maybe I need to start somewhere else in this particular case. And so I can always calculate the potential energy because I know the height. So the mass was 2, gravity is 10 meters per second squared, and I am at a vertical position of 15 meters. So 2 times 10 times 15 is 300 joules. So I can fill in my table here that the potential energy at the 15-meter mark is 300 joules. I know that the potential energy plus the kinetic energy has to equal 400. So I should be able to fill in a value here for what the kinetic energy is, so that adding the two potential and kinetic will give me 400. Or more specifically, I can rewrite the total mechanical energy is equal to kinetic plus potential. I can move the potential energy term over to the other side, and I know the kinetic energy is just the total energy subtracting off what the potential energy would be. So my kinetic energy at the 15-meter mark is going to be the total energy, which is 400, subtract off the 300, and I get 100 joules. Right? So this piece for the potential plus the kinetic has to equal 400 joules. Once I know the kinetic energy of my system, I can figure out what the speed is, because if I know the kinetic energy and the mass, the speed is just the square root of 2 times the kinetic energy over the mass. So this would be 2 times 100 over 2 kilograms. This would be the square root of 100, which is just 10 meters per second. So if you recall vertical motion, when an object is dropped, after 1 second, it falls a certain distance, and its speed has increased from 0 to 10 meters per second. So obviously, if it started from rest and it's traveling at 10 meters per second, this must have been, if it started at 20 meters and went to 5, this must have occurred in 1 second, because the speed of an object increases by 10 meters per second every second as it falls. We also learned, and this is going to come up in another slide, that the distance is 1/2 gravity times the time squared. And so after an object falls 1 second, we also could figure out the distance that it falls is 5 meters. And so, and this is from previous lectures, but here, how far did it fall? Well, it started at the 20-meter mark. It's at the 15-meter mark, so it fell after 1 second, essentially. It fell 5 meters. So this is making sense according to other things that we have discussed in previous lectures. All right, so we can go through the same process for the other points. I'm going to go through this a little more quickly. So at the 10 meters off of the ground, I can calculate the potential energy. It is 2 kilograms times 10 times the 10-meter mark, which is 200 joules. This is actually the halfway point, right, from the highest position to the lowest position. So at the halfway point, the potential and kinetic energies are exactly equal, and they're halfway between the total energy of the system. So I know that, that if I add these two values together, they have to add up to 400. So if I know the potential energy is 200, I can calculate the kinetic energy also has to be 200. And then once I know the kinetic energy, I can figure out the speed, the square root of twice the kinetic energy over the mass. So 2 times 200 over 2 kilograms is the square root of 200, and so the speed there would be 14.1. If I get to the 5-meter mark, I can go through the same process. I could calculate the potential energy, knowing that I'm at the 5-meter mark, so 2 times gravity times the position above the ground, which is 5 meters, would be 100 joules. If this is 100 joules of energy for potential energy, then, and I have to add potential and kinetic and get 400, then I know that the kinetic energy is going to have to be 300 joules. And then once I know what the kinetic energy is, I can calculate the speed as I've done before, and I end up with 17.3 meters per second. Finally, I basically am almost on the ground. So this is just before the rock hits the ground. I can calculate the potential energy, and right before it hits the ground, my position is 0, so my potential energy is 0. That means that my kinetic energy has to be 400 joules because the total energy is the potential plus the kinetic. And then I can calculate the speed as I've done before. 2 times the kinetic energy over the mass, square root of 400 is giving me 20 meters per second. So as we look at this table, we realize that the object started off with all potential energy and no kinetic energy. As it fell, it lost kinetic energy, so the kinetic energy decreased as it fell, and as it fell, the kinetic energy increased. Right? So decrease in potential energy, increase in kinetic energy, and but the total energy of the system stayed exactly the same because mechanical energy was conserved. We also notice, of course, that if the kinetic energy is increasing as it falls, the speed is also increasing, and we know that it should increase. By the time the speed gets to 20 meters per second, this must have been at a time of 2 seconds, because the object was dropped at time t equal to 0. After 1 second that goes by, the speed is 10 meters per second. After 2 seconds that go by, the speed should be 20 meters per second. After 3 seconds, it should be 30, and 4 seconds, 40, and so on. So I know that from our previous understanding of motion that this time here that the object ends up almost on the ground has to be at 2 seconds. I also realize that the object has fallen 20 meters. And that also makes sense because according to vertical motion, the distance that the object falls is 1/2 gravity times the time squared. If you put in 2 seconds, you would actually get 20 meters. So everything is sort of still making sense according to things that were learned in the past. So just sort of a summary of results, which I mentioned already. As the object falls, it's going to gain kinetic energy, and at the same time it loses potential energy. But the total mechanical energy of the system remained constant. At the halfway point, half of the energy was kinetic and half of it was potential. At the very lowest position, all of the energy is converted into kinetic energy, the potential energy is 0, and the speed is the greatest just before impact. I also mentioned that as it falls, when it's at the 20-meter mark, it has fallen for 2 seconds, and I could use the 1/2 gt squared, and I would figure out that distance would represent 2 meters, and its speed should have increased by 10 meters per second every second that goes by. So at the very bottom, it is traveling at 20 meters per second. So basically going back to those pictures that we looked at for vertical motion, everything makes sense in terms of the speed that the object has as it falls a certain distance.